In this lecture, we look at limits as x, the input, goes to infinity. The expression, the limit as x approaches a of f of x, is interpreted as asking what about f of x as x gets close to the real number a. As x gets close to a, what does f of x get close to? But we can also have the input variable x grow without bound, heading off towards infinity. The expression, the limit as x approaches infinity of f of x, means that we're asking about f of x as x approaches infinity, or more precisely, as x gets larger and larger, moving past numbers like a billion, or a billion billion, or even numbers like a Google, or a Googleplex, or even larger. By the way, I've misspelled Google there. Google should be Googol. Infinity is a mathematical concept, not a number, but at times mathematicians attempt to analyze and manipulate infinite quantities. In this class, we'll view plus infinity, or just infinity, as the concept of beyond all positive real numbers, larger than any number. We view minus infinity then as the concept of below or smaller than all negative numbers. We can find limits as x goes to infinity by estimating them with our calculator or by making an algebraic computation and argument. Here's a worked example. Let's use our calculator to create a table of values to figure out the limit as n goes to infinity of this quantity 1 plus 1 over n to the n. The input is n, it's growing beyond all bound, and the output is 1 plus 1 over n to the n. So I can start off making a table of values. I might try n as 5, and when I plug that into the function, I get 2.48 something. If I try n as 10, I get 2.59 something. N is 100, I get this. N is 1,000, I get that. As n gets larger and larger, notice that on the right side, the function is beginning to settle down onto a particular number. If I keep plugging in larger and larger numbers, I'm getting things like 2.71828, 1828, and so on. So the limit of this, as n goes to infinity, of this expression seems to be about 2.718, 2818, 2845. Indeed, the limit here is the number we now write as e, which to 50 decimal places, just in case you're curious, is this expression. By the way, a nice place to do computations of this type is Wolfram Alpha. On the PDF file, you can click on this link or just Google, Google, Wolfram Alpha. At Wolfram Alpha, you can type in a statement like e to 100 decimal places and see what happens. The limit as x goes to infinity of 1 over x is the number approached by this fraction 1 over x as x grows larger and larger beyond bound. This is an important limit we need to know. We want to know the limit as x grows beyond bounds of the expression 1 over x. If x is a million, then 1 over x is a millionth. If x is 10 to the 10th, 1 over x is 10 to the minus 10. That is an expression with 9 zeros and a 1 after the decimal place. If x is a Google, I misspelled it again, then 1 over x is 10 to the minus 100th, and so on. In decimal notation, that would be 99 zeros followed by a 1. With this experimentation, it should be clear that as x grows beyond bound, 1 over x shrinks to 0, so the limit is 0. Again, the limit of 1 over x as x goes to infinity is 0. We need this fact in some later computations. We interpret this equation as saying as x gets large beyond all bound, 1 over x gets close to 0. Or I can get 1 over x as close to 0 as I wish by letting x get arbitrarily large. Let's compute this limit. Let's use our calculators. If we try large numbers such as x is a billion, or x is 10 to the 10th, or whatever this number is, then f of x will be this, which, if my calculator will handle all the digits, will be this. And so the limit turns out to be 1.3 repeating. I can get limits by plugging in large x values and approximating our answers. It is clear that as x gets large, 4x squared in the numerator begins to dominate and to wipe out smaller terms like 5x minus 1. Similarly, in the denominator, if I look at the denominator and plug in large numbers, eventually 3x squared is much, much larger than 7x, and so minus 7x becomes irrelevant. If I think about doing this problem without a calculator, I can understand that this limit is the limit as x goes to infinity of 4x squared over 3x squared. I've thrown away the smaller terms. And of course, 4x squared over 3x squared simplifies to 4/3. The limit as x goes to infinity of 4/3 is just 4/3 because there's no x in it. We can make these computations precise algebraically. In this course, you will be asked to compute some limits algebraically, and when you do that, we're not using a calculator, but surely we're going to be using this fact. So for example, we can take this expression, rewrite it by multiplying numerator and denominator by the reciprocal of the highest power that appears. So x squared appears in the denominator, so let's multiply numerator and denominator by 1 over x squared. If we multiply numerator and denominator by 1 over x squared and simplify, we will get this, which simplifies to this. Written this way, the impact of the term 4x squared and 3x squared are clear. The other terms, which have an x in the denominator, will go to 0. As x gets large, 5 over x, or 1 over x squared, or 7 over x will all go to 0. So here's the evaluation of this limit using algebra, not a calculator. Here's the limit we want to do. Multiply numerator and denominator by 1 over x squared using the reciprocal of the largest power of x that appears in the denominator. I'll clean that up with our algebra, and then note that when there's an x in the denominator here, we're going to get a 0. So the limit is the numerator becomes 4, the denominator becomes 3, so our answer is 4/3. So we computed this limit using algebra. One more. Let's take this limit using algebra. Here the variable is k instead of x. That's all right. If I multiply top and bottom by 1 over k squared and clean it up, the numerator becomes 5 over k squared minus 1 over k squared. The numerator is 5 over k minus 1 over k squared. The denominator is 3 minus 7 over k. And so I'm going to get 0 over 3, which is just 0. One more example. Here's a more complicated problem that appears in one of the exercises. It's more complicated because it has a square root in it. Again, I can multiply by the denominator by 1 over x. I'm going to think of the square inside the square root as suggesting a simple x. If I multiply numerator and denominator by 1 over x, then I get this. And now the numerator is going to become a 5, but the denominator, what happens to that is involves a little bit more algebra. And this is a common question from some of my students, so I want to answer this. What happens when you multiply the square root of 4x squared minus 5 times 1 over x? How can we simplify that by putting everything under the radical sign? So the square root of 4x squared minus 5 times 1 over x, if I want to move 1 over x into the square root, I need to use the algebraic fact that as long as x is positive, the square root of 1 over x squared is 1 over x. So I'm going to replace 1 over x with the square root of 1 over x squared, so that I have square roots here, and then I'm going to use a property of square roots. The product of square roots is the square root of their product, so I can now put everything under the square root sign, and so this square root becomes the square root of 4x squared minus 5 over x squared, or the square root 4 minus 5x squared. So I can change that expression to that one. This algebra step makes it easy to compute the limit now. Here's my limit, multiplied by 1 over x. Run the 1 over x through numerator and denominator. Numerator is just 5, and the denominator becomes this expression. As x goes to infinity, certain things will go to 0. 20 over x will go to 0. 5 over x squared will go to 0. So my limit becomes this. The things with x's in the denominator became 0. And then I simplify that. 5 over minus 2, or minus 5 halves. In the next presentation, we explore limits where the output, y, goes to infinity.